Let's start with angles. So this angle here is clearly a quarter turn. So we could write that as a quarter of a revolution. So that's the most obvious way of recording an angle. A common convention is to use degrees, where 360 degrees is equal to 1 revolution. So then this angle becomes 90 degrees. Same deal. But 360 is quite an arbitrary choice. We've chosen it because it's a nice number. If you decompose 360, what do you get? 10 times 36. That's 2 times 5 times 6 times 6. We've got a 2 here, a 2 here, a 2 here, a 3 here, a 3 here, and a 5. So we've stacked 3 2s, 2 3s, and 1 5. So you can divide 360 lots of different ways. You can cut it in half, you could divide it by 8, you could divide it by 15, etc. It's a nice number to work with. But it's arbitrary. It's kind of, it could have been 720, it could have been any number of different things. A less arbitrary way to measure angle would be if we were to draw a unit circle and then just measure this arc length. Let's call that theta. Let's put in a 1 to show that's a unit circle. So, your angle, just this distance. And this is radians. So what is this distance if we go around a whole circle? 1 revolution corresponds to, well, you may know this as 2 pi. Better to write it as tau. So for a unit circle, the circumference is tau. There are tau radians in 1 revolution. So this original 90-degree quarter of a revolution, that's going to be tau over 4 radians. And these three are equivalent to one another, just different ways of writing the angle. I like radians very much because the unit circle comes back again and again in maths. So, challenge. If you add up all of the angles in a triangle, what do you get? You add up this, this, and this. What do you get? The answer is a half of a revolution, or 180 degrees, or pi radians. Notice I don't have to write radians. If I don't write anything, you assume radians. So this is the result you get on the back of a pencil case, but how do you show it? Well, let's try putting a circle around this point. And let's make a line that goes parallel with that original line, so that just indicates to us that they're parallel to one another. So, let's call these angles A, B, and C. Okay, so this angle is just the same as this angle, obviously. This angle is C, isn't it? That and that is the same as that and that because they're parallel. And this one's going to be B. That and that. Yes, this one's going to be B. And that one is opposite, so that's also B. And that's also going to be C. So you can see if you take any semicircle, it's going to contain A, B and C once. Let's just take this bottom one. I'm done. Let's see how many angles there are in a hexagon. If you add all the angles in a hexagon together, what are you going to get? I have to gauge this by eye because I don't have a protractor. Not too terrible. Okay, challenge. Pause the video now if you want to have a go at it yourself. Okay, so So next challenge is angles in a hexagon. Let's partition these off. Well, the fastest route is just to spot that this hexagon is just 6 equilateral triangles. Equilateral means equal length, so equal angle. So 3 of these make half a revolution, and we have 6 points and 2 per point, so we have 12 of them. So 3 of them make half a revolution, 6 of them make 1 revolution, 12 will make 2 revolutions, so 2 revs. Or if you like, 720 degrees, or 2 tau radians. If you had a more awkward shape, let's say an irregular 5-sided shape, maybe an irregular 4-sided shape. How to do this? So challenge, this is an n-gon. So angle in an n-gon. Here n equals 4. Okay, you can think of it this way. You can look at the external angles. So imagine you start here and you're looking in this direction. You have to turn in order to align yourself with this edge. Now you walk here, now you turn again, now you walk, now you turn again, walk, turn again, and you're back to where you started. Can you see that you've turned around once? If you hadn't done any walking, you just did the turning, you were looking east, now you were looking kind of south, now you're looking almost north, and now you're looking east again. You've done one complete revolution. So the sum of these angles is 1 revolution. This means sum of the black angles is equal to 1 revolution. This is a sigma, Greek sigma. We use it for sum, S for sum, sigma. Now, let's look at the complement of those angles. We've got a half turn 4 times. So the sum of the black angles plus the white angles is equal to 4 times a half rev. equals 2 revs. Therefore, the sum of the white angles must equal what? Just 1 rev. So there's 360 degrees inside a general four-sided object, a general quadrilateral. Quad 4, lateral side, four-sided object, 360 degrees, tau, radians, 1 rev. So challenge for you, what is the angle inside a general 5-sided object? I'm not gonna do that. It's just a challenge if you feel like it. Let's look at triangles inside circles. So that's a diameter passing through the center. And now let's take any arbitrary point on the circle and let's connect to make a triangle. This looks rather like 90 degrees. Can we prove it? So, challenge for you. If you'd like to pause, then have a go. Here's a hint. You often end up doing this with these kind of problems. You split your triangle into 2 isosceles triangles. An isosceles triangle has 2 sides of equal length. And this is a unit circle. So that length is 1, that length is 1, that length is also 1. So because the lengths are equal, this means the angles are equal. Let's call this alpha, alpha, beta, beta. Does that make sense? So we know from here that alpha plus beta must equal half a revolution. So alpha plus beta must equal a half of a revolution. But that is just 2 lots of alpha plus beta. So therefore, alpha plus beta must be a quarter of a revolution. So that angle there, alpha plus beta, is a quarter of a revolution. And for a right angle, you don't do the angle as an arc, you do it as a corner box. Okay, so that's pretty cool. Start off on the diameter, pick any point, you'll get a right angle. I'm not sure what heading to give this because it's a bit wordy. This angle is the inscribed angle. Basically, if you pick 3 points on a circle and make an angle, then it's called an inscribed angle. And so this is an inscribed angle where two of the points are a diameter, so inscribed angle using diameter is equal to a quarter of a revolution, 90 degrees. Or you get a right-angled triangle. It's easy just to see it. It's just going to create trouble putting into words. Let's do another one. Okay, so we pick any 3 points on our circle. I'm going to be careful not to make them look symmetrical. Let's pick that one a bit closer to there than it is to there. Now we're going to show that if this is theta, then this is 2 theta. If you'd like to, pause the video and see if you can figure it out yourself. Okay, again, the hint would be to again create 2 isosceles triangles. So we've got alpha there and beta there and beta there. So we're going to try and show that this thing is 2 alpha plus 2 beta. Okay, so let's call these A and B. And we know that A plus alpha is half a revolution, and B plus beta is another half of a revolution. So adding them all up, A plus alpha plus B plus beta is going to equal a whole revolution. And also from the around this point, A plus B plus 2 theta, well, we don't know this yet. We should put a question mark. A plus B plus question mark is also equal to 1 rev. So that question mark must equal alpha plus beta. Done. Okay, there's just enough paper left for some ruler and compass constructions. Let's start off with a simple one. So the challenge is, it's straight edge and compass, not ruler and compass, because we're not allowed to use the fact that we've got numbers marked at regular intervals. It's just a straight edge. So challenge is, given 2 points, I should probably draw this one a bit lower down. There we go. Given 2 points, using only straight edge and compass, can you bisect that line segment between them? Can you find a point that's exactly midway between them? Challenge for you. Okay, so why don't we set our compass? Oh, and you're not allowed to set your compass to anywhere. You can only set it to a distance you've already got. So the only distance we've got is that distance between the points. And as you can see, I've gone off my diagram a little bit. Haven't quite gauged that one right. So now this yields 2 more points, and if we connect these together and these together, we have the midpoint. So this is straight edge and compass constructions. So a more interesting one might be, given two line segments, bisect the angle, cut the angle in half. Again, have a go. You learn from doing stuff rather than watching someone else do stuff. So if you really are keen on maths, then be always ready on the pause button. See if you can figure out, maybe you'll come up with a different way of doing something. There's often more than one way to do something. So I'm going to set my compass to the shorter of the two, and I don't need to clutter the diagram with lots of circles, but I'm going to mark off that point. Now, I've got a feeling if I draw a circle around that point and around that point, it's going to intersect in two places, and I can't quite see it to the end, but I think it's going to work. So let's now set my compass to that gauge and draw a couple of circles. And it looks as though that's going to be halving the angle. You might want to think about why that actually works. As in, clearly it seems to work, but why is it actually working? So I'll leave that as a challenge. Okay, so that will serve as a really basic introduction to geometry. We've covered what is angle, different ways to measure angle, radians, degrees, revolutions. We've shown that a triangle contains half a revolution of angles, a hexagon contains 2 revolutions of angles, a square contains 1 revolution. You should be able to take any irregular n-sided object and figure out how many revolutions it contains. And we've shown that if you start with a diameter on a circle and pick any point on the circle's circumference, you get a right angle triangle. We've shown that if you make any triangle on a circle and connect it into this shape, this angle is twice this angle. Let's put that into theta. And finally, we've done some basic straight edge and compass constructions. As a final note, there's a very famous problem which is trisecting an angle using straight edge and compass, and it's something a lot of people have tried to do, even though it's been proven that it can't be done. And there's a basic 2 against 3 problem going on, like 2 to the 4 is 16, 2 to the 5 equals 32. You're never going to get a 3 in this number. You're never going to get a number that's divisible by 3. That's not an explanation, that's just a small fraction of very tricky proof, to be honest. So yeah, you're limited in what you can construct with straight edge and compass. Okay, thanks for watching.